So this is the AQA C3 Unit C3 Chemistry, May 2015. It's a 60-mark paper, just like the C1 and the C2. This paper is a bit longer though, in terms of the amount of questions that it's got. It's actually got 8 questions, obviously testing all the different topics in C3. So just go get cracking with it. So question 1, it says figure 1 shows the position of 8 elements in the modern periodic table. Choose the correct chemical symbols from figure 1 to complete each sentence. The 2 metals that react vigorously with water are something and something. So what you need to do is think back right when you started looking at C3. It's these 2 metals here in group 1. They both react vigorously with water, lithium and potassium. Obviously they give off hydrogen gas and make a alkaline solution, hydroxide of each metal. But it says in the question just to put the symbols, so we can just put lithium and potassium. Next question, the element used as a catalyst in the Haber process is, it's this one here, just one you have to remember, iron. It's one of the 4 conditions that you have to remember in the Haber process. And then 1C, the 2 elements with 5 electrons in their outer shell, highest energy level R. It's in this group here. It's obviously 5 in their outer shell, so it's nitrogen and arsenic. Again, I'm just putting the symbols rather than writing the elements' names out. And finally, iron has ions with different charges. The other metal that has ions with different charges is it's this one here. It's copper. One of the transition metals. They're all known for having different oxidation states or different charges. Easy 4 marks there. Question 2. In 1866, John Newlands produced an early version of the periodic table. Part of Newlands' periodic table is shown in figure 2. We've got it here in all its glory. It says Newlands' periodic table arranged all the known elements into columns in order of their atomic weight. Newlands was trying to show a pattern by putting the elements into columns. Iron does not fit the pattern in column 7. Give a reason why. And this is obviously one of the problems with his periodic tables. For Mendeleev came along and had his way. If you look here, we've got oxygen, we've got sulfur. They're both non-metals. Iron is a metal, so you can just get a nice easy mark for that. Iron is a metal. I guess you could put oxygen and sulfur are not. 2b. In 1869, Dmitry Mendeleev produced his version of the periodic table. Why did Mendeleev leave gaps from undiscovered elements in his periodic table? So obviously this was one of his genius ideas that he had when he was coming up with his own periodic table, to leave gaps, because he had the wisdom to sort of understand that we might not have discovered all the elements. But if he left gaps, that allowed him to actually group elements together. Oops, sorry about that E. Elements together with similar properties. Basically allowed them to fit the pattern. Oop. Properties. You probably get the mark actually for writing that as well, fit the pattern. 2C. Newlands and Mendeleev placed the elements in an order of atomic weight. Complete the sentence. The modern periodic table places the elements in order of, we now do it on our periodic table, atomic number. So the number of protons. 2D. Lithium, sodium, potassium are all in group 1 of the modern periodic table. Explain why. Or we can go back to the first question that we looked at. And we know that all of them have 1 electron. 1 electron in their outer shell. And we can also think back that when you put them all in water, they all react vigorously. They're all soft metals. They all have, and just how Mendeleev wanted, they have similar properties. A nice easy 2 marks there. Question 3. This is about the halogens, group 7. How do the boiling points of the halogens change down the group from fluorine to iodine? Or you should know, even if you don't have any basic knowledge of this topic, is fluorine is a gas at room temperature, and we know iodine is usually a solid at room temperature. So using those two things, you can deduce basically that as you go down the group, the boiling point increases. Obviously down the group it increases, but just say it on the question, so that'll give you the mark. Sodium bromide is produced by reacting sodium with bromine. Sodium bromide is an ionic compound. Write down the two symbols of the two ions in sodium bromide. So it's easy to get caught into the trap of just writing the symbols. This is where you use your data sheet. Just flip it over. You can see that sodium is Na plus and bromide ions are Br minus. So they cancel out. You can obviously work that out without the data sheet. Sodium loses its outer shell electron. It's in group 1, becomes Na plus. Bromine gains 1 in its outer shell to become Br minus. Chlorine reacts with sodium bromide solution to produce bromine and one other product. Complete the word equation for the reaction. So chlorine plus sodium bromide is bromine. Well, this is obviously a displacement reaction, even says in the question below. So chlorine effectively kicks out the bromide, leaving bromine, and we make sodium chloride. Not strictly a C3 question, that's more of a C1 question, but obviously knowledge is the same across all three. Why does chlorine displace bromine from sodium bromide? Well, if you remember, chlorine is just much more reactive. It's more reactive than bromine, so it can displace it. Obviously chlorines, they've both got 7 electrons in their outer shell, but the outer shell electrons of the chlorine are much closer to the nucleus, so it's much better attracting electrons compared to the bromine. Use the data sheet to answer out this question, so obviously make sure you use the data sheet. It says suggest which halogen could react with sodium chloride solution to produce chlorine. You just look on the data sheet, you can see that you've got bromine, then you've got chlorine, and then it will be fluorine, which is the most reactive of the halogens. Fluorine, again, 1 mark question there. Right, question 4. This is about water, so we get to the exciting stuff now. Rainwater is soft. How is hard water produced from rainwater? So, question's looking for you to describe what 2 things can make water hard. So it's either Mg or Ca ions dissolved in the water, and this is normally from rocks. I believe on the mark scheme it says as well you can get away with writing limestone if you're talking specifically about these ions, so you can put this, but I think just writing the symbols and the ions would be fine as well. 4b, in this question, it's a 6-mark question, so you obviously got the UCC sort of guidelines to that. It says hard water can be softened by 2 different methods. Method 1, ion exchange, and method 2, adding sodium carbonate, washing soda. And you've got the 2 methods sort of illustrated there. Describe how each method softens water and compare advantages of these 2 methods. Okay, so we'll just start with the softening water. Involves removing Mg or Ca ions. That's what it does. So that's how you obviously soften water. You getting rid of those 2 dissolved ions to make it soft. We'll start with the ion exchange column. So ion exchange column. So that has a resin, which usually contains either Na plus or H plus ions. Exchange with the Mg or the Ca plus ions. Obviously making water soft. Making water soft. Now obviously the question is looking at the advantages of these methods. So what's an advantage of having this ion exchange column? So if you look up here, you can see you can pour your hard water in, keep pouring in your hard water, and out comes the soft water. So it's sort of a continuous process. So I can put that there as another bullet point. Sorry about my handwriting. Continuous process, and obviously it's also quite quick as well. Now let's talk about the sodium carbonate solution. Well, add in the sodium washing soda. So with the sodium carbonate solution, sorry, going back down, try and change colour pen. Oh, that's horrendous, that one. Sodium carbonate. Oh, sorry about that. Sodium carbonate. So adding the sodium carbonate. So adding sodium carbonate or adding soda. Precipitates out, so that means they sort of come out as a solid. MgCa ions in the form of their carbonates. So e.g. we could do magnesium carbonate. You wouldn't need to know the formula, I'm just writing it there. So adding soda precipitates out the magnesium calcium ions in form of their carbonates. What are some advantages of this? Well, adding sodium carbonate, it's a really easy process. So easy process, you just add it. Easy process. And compared to having to buy this resin, it's actually very, very cheap, which is another advantage. And I see no reason why that wouldn't get you all the 6 marks. You've talked about how water's been softened. You've got this ion exchange column here, describing how that works. And then you've got your sodium carbonate and how that works, and the advantages of each as well. Just change back to my red pen. So then we've got, this question is about organic compounds. Ethanol is an alcohol. One use of ethanol is in alcoholic drinks. Give 2 other uses of ethanol. Well, one of the main uses is as a solvent, so we use it to dissolve things inside it in chemical reactions. And another use is actually we can use it as a fuel, so it's in certain fuels as a sort of a biofuel, something we can actually grow, a renewable fuel. Which gas is produced when sodium reacts with ethanol? It's this one here, hydrogen. Obviously you test that with a lead splint, get a squeaky pop. Ethanoic acid can be produced from ethanol. What type of reaction produces ethanoic acid from ethanol? We use an oxidizer. This is an oxidation reaction. Kind of something you just have to remember really well if you don't actually understand the process of it, which is something you'd probably look a bit more in A-level. 5C, complete the displayed structure of ethanoic acid. So here you've been given the displayed formula of ethanoic acid, so you can just translate that. So you've got the CH3 here. You have to remember the functional group of this, and it looks a bit like this. So you've got your double bond, and then you've got your O, and then you've got your H. Okay, and that's obviously showing you've got a carboxylic acid there. Right, so question 5C. Solutions of ethanoic acid and hydrochloric acid with the same concentration have different pH values. Explain why the solution of ethanoic acid has a higher pH than the solution of hydrochloric acid. So we can look here. I think of steam notification. You can look here. It says it has a higher pH. So this is the first thing we have to see. This is less acidic. The higher the pH you go, the more alkali it becomes. The lower the pH you have, the more acidic. So we can actually use that for our first point. So ethanoic cannot spell today. Ethanoic acid is weaker or less acidic because it does not, and this is the key point, it does not ionize completely. It does not ionize completely. So the H plus ions that leave, if we go back up to the structure, the H plus ions that leave off here to make it become acidic, it's actually in equilibrium, so they can go backwards and forwards, whereas in HCl it's more of a final completely ionize or completely disassociate. 5D, ethanol and ethanoic acid react in the presence of a catalyst to form an ester. Name the ester made from ethanol and ethanoic acid. So this is where you use this part here, so it's ethyl, and then ethanoate for the ester part. Ethyl ethanoate. What type of chemical is used as a catalyst in this reaction? Well, it's an acid that we use to do that. Normally sulfuric acid. Esters are used in perfumes because they smell pleasant and are volatile. What does volatile mean? Well, it means they evaporate easily. They easily turn into a gas. Question 6. This question is about reversible reactions and chemical equilibrium. Reversible reactions can reach equilibrium in a closed system. What is meant by a closed system? So, closed system, basically just how it sounds. Nothing can leave or enter the system. So nothing can get in or nothing can get out. 6a, part 2, explain why when a reversible reaction reaches equilibrium, the reaction appears to have stopped. So the reaction appears to have stopped. Now, 2 marks. The first thing is, obviously, it's asking for your understanding of an equilibrium. So at equilibrium, the forward and backwards reactions happen at the same rate. And I managed to mess that up well and truly. Happens at the same rate. Forward and backward reaction have the same rate. So therefore the overall quantities, so how much you've made, will remain the same. Will remain the same. And that's straight off the mark scheme, but it makes sense, will remain the same. So forward and backwards reactions happen at equilibrium, so you've got the 2 reactions backwards and forwards, happen at the same rate, so either side the quantities don't change. In the Haber process, the reaction of nitrogen with hydrogen produce ammonia is reversible. Name a natural resource from which hydrogen is produced. There's a few where we can get hydrogen. I think the main one it's probably looking for is natural gas. So there's bits of hydrogen locked up in there, natural gas. You can have methane. It does say, I've just checked the mark scheme, it does say allow water as well. Obviously you could run electrolysis on some water to get hydrogen as well. I think it's a lot cheaper to get it from the natural gas than using all that electricity. So the Haber process uses a catalyst to speed up the rate of reaction. Explain how a catalyst does this. Well, a catalyst, first off, it lowers the activation energy. This is straight from C2. Lowers the activation energy, providing, and this is the second mark, an alternate reaction pathway. So just another route that the reaction can take with much less energy, so it happens much quicker. What happens to the amount of ammonia produced at equilibrium if the pressure is increased? Give a reason for your answer. So you're going to have to look at this equation up here. And if you look on this sort of left-hand side, you've actually got 4 lots of molecules. 3 lots of H2 and 1 lot of N2, and on the right hand side you've got 2 lots of ammonia. So if we increase the pressure of that system, the system's going to try and reduce that change, and the reaction is going to move to the right. It's going to move to the right because there's less molecules on that side. It's going to try and squeeze more into the same space, so it's going to move to the right. So give a reason for your answer. Give a reason for your answer. So amount of, I'm just going to write out that, ammonia increases, equilibrium moves to the right, equilibrium shifts to side with less molecules. 2 marks. The decomposition of hydrogen into hydrogen and iodine is reversible. The forward reaction is endothermic. Okay, so going from this way to this way. So endo. So obviously that way must be exo. The energy level diagram for the forward reaction is shown in figure 3. Draw an arrow to show the activation energy on the diagram in figure 3. It's going to be this, so all the way from the reactants. That's an awful arrow. It's going to be just there. That's your activation energy. These are these tricky questions that are quite easy to miss sometimes. Just drawing a simple line gives you a mark. Sometimes you can skip past it because it just looks like a diagram. So how does the diagram in figure 3 show that the reaction is endothermic? So if we look, these are our reactants and these are our products. You can see that the products have actually got more energy than the reactants, so they must have taken that energy in from the surroundings, meaning it's an endothermic reaction. So products have more energy than reactants. I'll put taken in from surroundings, if I can type. You know what I mean, surroundings. Suggest what effect, if any, increasing the temperature will have on the amount of hydrogen iodide at equilibrium. Give a reason for your answer. Ooh, lovely question. So it says increasing the temperature on this reaction. So if we remember, going forward is endothermic, going backwards is exothermic. So we're going to be increasing the temp of this. So the equilibrium is obviously going to want to reduce that change. So if you increase the heat or increase the temperature, the equilibrium is going to move to the left. Move to the right. The endothermic favour the endothermic direction. So you're going to actually end up with more hydrogen and iodine and less hydrogen iodide. So I'll just put less hydrogen iodide. Equilibrium will favour endothermic. I should have dashed that reaction to reduce increase in temperature. This question is about chemical analysis. The student has solutions of 3 compounds X, Y and Z. The student uses tests to identify the ions in 3 compounds and records the results of the test in table 1. Okay, easy peasy, if you alert them and remember them. So it's a 3-mark question, effectively looking for 6 things, isn't it? So identify the 2 ions present in each compound. So we'll just do it methodically. We'll start with X. So X, flame test, no colour. While the They're always nice and easy, so that's why they've skipped that one. Green precipitate, you just have to remember it's iron 2 ions that cause that, and the white precipitate is sulfate ions. Why? Yellow flame, nice and easy. You should remember that that's a sodium ion, and a yellow precipitate is iodide ions. And then we go down to Z. No colour again, no flame test. Add sodium hydroxide. So this is your test for your transition metal. So it's either copper 2, iron 2, or iron 3. Brown precipitate, that's iron 3. And then a cream precipitate. Remember, white is chlorine, cream is bromine, yellow is iodine. So it's bromide. So I say bromide ions. So, I've skipped down a bit there. So, a chemist needs to find the concentration of a solution of barium hydroxide. Barium hydroxide solution is an alkali. The chemist could find the concentration of barium hydroxide using two methods. So, method 1, 25 centimeter cubed. Precipitate is formed. The precipitate is then filtered, dried, and weighed. The concentration of the barium hydroxide is calculated from the mass of the barium sulfate produced. Right, we'll talk about that one first then, and then we'll look at method 2. So method 1, so the first thing is it says, it's sort of giving it here, an excess of solution precipitate is formed, and then it's calculated from the mass of, okay, so firstly calculating them from the mass, which you're going to be weighing. So weighing is very accurate, and I'm shooting up there, accurate. So that's a massive plus point there, nice advantage. The precipitate is filtered, dried, and weighed. So problem with filtering is you could have filtering equals a loss of product. A bit of a disadvantage. And dried and weighed. Now this is one thing that I came across when I was doing my degree a lot. Things are rarely dry. So precipitate could still be wet. Again, that would give you an incorrect mass, and obviously make the concentration appear higher than it is, or lower than it is. Method 2. So the 25 centimeter cubed the barium hydroxide solution is titrated with an acid for no concentration. The concentration of the barium hydroxide solution is calculated from the result of the titration. So for method 2, oh, where's my pen? There it is. Method 2, well, one thing we know about titrations are accurate, very accurate, you use very precise, well, you use very sort of calibrated equipment for that, and it means that you can also work at the calculation from very low concentrations. Tricky question that, and there's basically two advantages as well. So 5 points, 5 marks. Yeah, that'd be enough for that to move on. And this question paper keeps on going. Question 8. A student investigates the energy released when hydrochloric acid completely neutralizes sodium hydroxide solution. The student uses the apparatus shown in figure 4, and it just looks like a typical dropping some acid into some base and measuring the temperature. Bit of calorimetry. So it says student measured 25 centimeter cubed, added it 5 centimeter cubed at a time, and stirs. Student has plotted a graph of results. The graph line has been incorrectly drawn, including an anomalous result. The graph is shown in figure 5. Suggest a cause for the anomalous result when 20 centimetre cubes of acid is added. Well, they haven't got a lid on the... I don't think they've got a lid. And there's no lid on there, so you could have heat loss. And if we're looking for a human error, I think stirring. So not enough stirring, I suppose you could put that. Insufficient stirring. Obviously it's only 1 mark, so it's only looking for 1. So suggest the true value of the temperature of the anomalous point. So if we were to draw a line, if we were to draw a line up there, I'd say probably 32. Probably a bit of leeway in that. If I look at the mark scheme, yeah, 32 to 33. What was the total volume of the mixture when the maximum temperature was reached? What was the total volume? Okay, so we're looking for the maximum temperature, which was there. So 30. Yeah, 30. Plus how much to start off with? 25. So 55. 55 total mixture. We could just do the workings out here as well. So 30 added plus the 25 that we started with equals 55. Calculate the overall increase of temperature in this experiment. So let's go back to this graph. It starts off here, which is 15, 16, 17, 18. Goes all the way up to I think that's 38. So 38 minus 18, 20 degrees C, sorry. Alright, okay, so use your answers to part A3 and A4 and the calculation to work out the energy released. So energy released is Q, so the mass of the solution times C times change in temperature. So we've got the mass, which is going to be 55, I could write it here, never mind, 55 times 4.2 times by 20. So I'm going to have to use a calculator for that. So we've got 55 times 4.2 times 20, and I get 4,620, I think. 4,620, yeah. And the unit of that is going to be energy released. Oh, there we go. Is joules. And then finally, the student did an experiment on page 19 again, started with 50 centimetre cubed. Sorry, the student did the experiment again on page 19, starting with 50 centimetre cubed of sodium hydroxide solution instead of 20 centimetre cubed. Explain why this would make no difference to the overall temperature increase. So, it's actually quite a simple answer for this one. If you double the amount of solution, you will sort of double, well, you won't quite double the energy out, so you will increase the energy given out. So the energy given out will increase, however, there is more solution to heat as well. So cancels out basically, so it doesn't make any difference because you are increasing the amount of energy that's given out, but you're also having more solution for the energy to heat up, so it ends up being the same. And that's the end of the paper. I hope that helps walking through it like that. Let me know in the comments if I've made any glaring errors or if it helped you. I will do some more.